Section 4.2, Integer Exponents and the Quotient Rule. Last time we looked at several rules of exponents. We're going to add to that list now. And I'll go ahead and tell you, I'm going to take this section a little out of the order in which she presents the material, but we still come up with the same set of rules for exponents. Now, last time we had discovered that if we have a product of like bases, we can add those exponents because we're counting up how many factors we have of that like base. It would make sense, wouldn't it, that if when we multiply like bases, we add the exponents, that if I were to divide like bases, perhaps I will subtract the exponents. Before we develop that, I want you to consider this method of reducing fractions. It's like cross-canceling, but actually showing all of the factors. 4 is 2 times 2. 6 is 2 times 3. And we can cancel factors that are common to the top and bottom. We're really just cross-canceling. So with that idea in mind, let's investigate what's going to happen when we have a quotient of like bases. If we treat this in a way similar to how we did the last section and expand our exponential expressions, what we have is 7 factors of a in the top of this fraction and 3 factors of a in the bottom. Now, when I'm done reducing this, when I'm done canceling factors of a that are common to the top and bottom, how many factors of a are left and where are they? There are 4 factors of a left in this numerator. That's a to the 4th. It would be over 1. We don't write over 1. So looking from top to bottom, it does appear that we can subtract those exponents. And it makes sense when we think of it in terms of this idea of canceling. There were 7 on the top, 3 on the bottom. When I'm done canceling, when I'm done reducing, how many will be left? And where will they be? So this leads to our first rule, which, like I said, I'm taking this a little out of order. So we're going to jump to page 274. Page 274, brown box in the middle, the quotient rule for exponents. It says a to the m over a to the n equals a to the m minus n. And again, that's no surprise. A product of like bases, we add the exponents. A quotient of like bases, we subtract the exponents. But investigating this quotient rule a little further leads to some interesting things. What if I have something like b squared over b to the 6th? Now, if I were to work this the same way I worked the last one, that is, expand the top and the bottom, that's 2 factors of b over 6 factors of b. And when I'm done canceling, how many will be left and where will they be? 4 factors of b will remain in the bottom. What's left over in the top? Nothing. But this is what? This is a multiplicative nothing. So we're left with that residual factor of 1, and in the bottom, b to the 4th. But didn't we just have a rule that says if I have a quotient of like bases, I can subtract the exponents? In other words, this is b to the 2 minus 6, or b to the negative 4. Well, if this is equal to 1 over b to the positive 4th, and it's also equal to b raised to the negative 4th, then these two things must be equal to each other. What does that tell me about a negative exponent? It tells me that that negative indicates a reciprocal. That negative indicates a reciprocal. In other words, these 4 factors of b don't really belong in the numerator. Because this is what? This is b to the negative 4 over 1. They don't really belong to the numerator. They belong to the denominator. So we reciprocate. We take the reciprocal and put that b to the 4th in the denominator. Likewise, if I had something like x to the negative 1, that would be 1 over x to the positive 1, and we don't show a power of positive 1. Y to the negative 2 is 1 over y squared. We take the reciprocal, and that's what that negative indicates. This gives us the next rule that I want to take a look at. Here on page 271, and she says, for negative exponents, a to the negative n equals 1 over a to the positive n. In other words, those factors belong on the other side of the fraction bar. They belong on the other side of the fraction bar. Well, if that's the case, let's think about this. C to the negative 4 over D to the negative 3. Simplify. Now, in this section, we're going to add to our rules of simplification. We know from chapter 1 that to simplify means fractions must be in lowest terms. We know that we have to remove grouping symbols. We have to perform all operations that can be performed, and so on. Now, it also is a rule that in a final answer, I can have no negative exponents. Exponents in a final answer should be positive. Otherwise, it's not considered simplified. C to the negative 4. Well, a c to the negative 4 in the numerator is actually a c to the positive 4th in the denominator. And by that same token, a d to the negative 3 in the bottom is actually a d to the positive 3 in the top. And so we can now say that this is simplified. While we're talking about fractions, let me go ahead and do this one. Let's say I have some fraction raised to a negative power. Well, we know from the previous section I can distribute this power in on the top and bottom of my fraction. This would give me g to the negative 2 over h to the negative 2. And then what can I do with these negative exponents? G to the negative 2 in the top becomes g to the positive 2 in the bottom, while h to the negative 2 in the bottom becomes h to the positive 2 in the top. Now this is simplified. Okay, this is simplified. But I want to go one step further. I want to undistribute that power of 2. I want to pull it back out. In other words, this can be written as h over g raised to the positive 2. Not sure about that? Distribute the 2 back in. Returns you to the previous step. Now look from beginning to the very end. And what do you see happening? If I have a fraction raised to a negative power, it's the same as his reciprocal raised to that positive power, which makes sense because we've determined that a negative exponent indicates a reciprocal. A couple more rules. Page 273 in the brown box, middle of the page. She says if we have a to the negative m over a b to the negative n, that's the same as b to the positive n over a to the positive m. And that's what we discovered working our C and D problem. And in this same box, because it really has to do with the same thing, she says if I have a fraction, a over b, raised to some negative power, that's just that same fraction's reciprocal raised to that positive power. There's one more thing we have left to discover as we consider this quotient rule for exponents. Something that we haven't looked at yet. What if I have something like x to the fourth over x to the fourth? Well, x to the fourth over itself, anything over itself, is 1. But in the light of our quotient rule, we could say what? That this is x raised to the 4 minus 4, which is x to the 0. Well, if this is equal to 1, and this is also x to the 0, then x to the 0 must be equal to 1. Of course, x itself could not be 0 because of where this comes from. That would give me a 0 in the denominator. So now, back at the beginning of the section, page 270, at the bottom in this brown box, it says for any non-zero real number a to the 0 is 1. But a can't be 0. I mean, think about this. 0 raised to any power. 0 times 0 is 0. 0 raised to any power. 3 factors of 0. 0 times 0 times 0 is 0. But if I have something raised to the 0 power, according to this rule, it's going to be equal to 1. If I have something raised to the 0 power, it's going to be 1. And so, let's think for just a second, what is 0 raised to the 0 power? Well, 0 raised to any power is 0. Anything raised to the 0 power is 1. And this is actually a much more complicated problem than that. In fact, we'll wait until we get into some calculus a few semesters down the road before we talk about that again. It's actually called an indeterminate form. An indeterminate form. We're not going to concern ourselves with it. But this is one reason that she says in the box, any non-zero real number raised to the 0 power will give me 1. I want to see if this all makes sense in the light of some numeric examples. Let's think about this pattern. 2 to the third. 2 times 2 times 2 is 8. 2 squared. 2 times 2 is 4. 2 raised to the first power. One factor of 2 is just 2 itself. 2 raised to the 0 power. What's happening? Each line that I come down, I'm losing a factor of 2. So what happens to my answers? They get cut in half. Makes sense? Well, cut this answer in half. And that would imply that 2 raised to the 0 power is 1. If I have 2 factors of 2, I get 4. If I have a single factor of 2, if I have a single 2, I've just got 2. If I have no factors of 2, now listen to this. If I have no factors of 2, then I have nothing. But what kind of nothing? A power indicates repeated multiplication. I have the multiplicative nothing, the multiplicative identity 1. And so it even makes sense in light of that. Let's keep going. 2 raised to the negative 1. Well, cut this answer in half again. Half of 1 is a half. Does that make sense? Well, a negative exponent means take the reciprocal. This is 1 over 2 to the first power, which is 1/2. 2 raised to the negative 2 would be 1 over 2 to the positive 2, 1/4, which is half again. So yeah, this makes sense. This pattern holds. 10 to the third, 10 squared. 10 to the first, 10 to the 0, 10 to the negative 1, 10 to the negative 2. 10 cubed, 10 times 10 times 10, 1,000. 10 squared, 10 times 10 is 100. 10 to the first, that's just a 10. 10 to the 0, anything to the 0 power is 1. When I say that, we understand that I'm not talking about 0 to the 0 power. 10 to the negative 1 is 1 over 10 to the first, which is just 1 over 10. 10 to the negative 2 would be 1 over 10 squared, which is 1 over 100. Now look at the pattern. Every time I drop down, what am I doing? I am losing a factor of 10. So every time I drop down, I'm cutting this by a factor of 10. What am I doing? I'm dividing by 10. If I'm losing a factor of 10, I'm dividing by 10. 1,000 divided by 10 drops me to 100. Divided by 10 drops me to 10. 10 divided by 10 drops me to 1. The multiplicative, nothing, for no factors of 10. Divide 1 by 10. That'd be a tenth. Divide by 10 again, you're down to a hundredth. And so the pattern holds. And this idea of integers for exponents, meaning now I'm throwing in the 0 and I'm throwing in the negatives, the idea holds as we look at these numerical examples. Now here toward the end of the section, on page 275, she now summarizes all of the rules that we have, not only from this section, but from the previous section as well. And so here on page 275 in this large brown box, we have our product rule. Product of like bases, you add the exponents. Our zero exponent rule, which we just learned. Anything to the 0 is 1, except 0 to the 0, which we know we're not going to worry about that until calculus. Our negative exponent. Something to a negative is 1 over that thing to the positive. We take the reciprocal. My quotient rule, kind of a reflection of my product rule. Product rule says a product of like bases, I add the exponents. My quotient rule, a quotient of like bases, I subtract those exponents. We have our power rules. Remember, power rule A, I typically call power to a power. And when we have a power to a power, we multiply those powers. Power rules B and C that we talked about last time, those are our distributive rules for exponents. And our negative to positive rules, something raised to a negative power is that same thing to the positive, but on the other side of the fraction bar. And a fraction to a negative is its reciprocal to that positive. Our brown box here at the end of section 4.2, summarizing everything that we've put together so far. Join me now in the homework. And let's put these rules to work for us. We'll start with number 2. Now in number 2, notice the instructions. The only thing that we are asked to do, is to determine whether this answer would be positive, negative, or 0. Well, what do I have? I have a negative base. What's the base? That whole negative 3, because it's in parentheses. And it's being raised to an even power. A negative raised to an even power will have what sign for its final answer? Any negative raised to an even is going to be positive. Make sure you don't misunderstand. Has nothing to do, those two negatives cannot see each other. Those two negatives can't get together and cancel each other out. The reason that my answer is positive is because if we were to work this out, we'd say, well, this is 1 over that same base raised to the positive 2, which is 1 over, and I probably don't need to show this step, but negative 3 times itself. It's probably a mental step. There's the two negatives that get together. because my power was even. Had nothing to do with the fact that it was negative. This gives me a positive 1/9 for a final answer. But she only wanted to know what will the sign be on my answer. If we think about that one, the result will be positive because it's a negative raised to an even. That being said, what would the sign on this answer be? If I have a negative raised to some odd power, a negative raised to an odd power, we know from last time a negative to an odd will always turn out to be negative. If we were to work this one out, we would say that this is 1 over this same base raised to the positive 5th power, which would be 1 over 5 factors of -3 multiplied together. And what's going to happen? Every pair of negatives will turn positive, and there'll be one left over because it was an odd power. And so my answer will be negative 1 over, and whatever 3 times itself 5 times is. It happens to be 243, which is a fact that you will memorize when we get to chapter 5. This is negative because a negative to an odd is negative. Look at number 6. And again, we should be able to answer these, positive, negative, or 0, without actually working most of these out. 1/5 to the -2. I have a positive number raised to some power. I don't care what power it is. I don't care if that power is positive or negative or 0. If I have a positive number raised to a power, the result is going to be positive. Now, how would that work here? Well, a fraction to a negative is the same as its reciprocal to the positive. The reciprocal of 1/5 is 5. It's 5 over 1, but we don't write over 1. So it's the reciprocal to the positive. And a positive number to any power is going to be a positive answer. How about number 8? Now this one we really have no way to do this but to crank it out. So order of operations, here we go. This is 1 minus 7 raised to the 0 power. We'll do the power before we subtract. 7 to the 0, anything to the 0 is 1. And 1 minus 1 is 0. So my answer here, is it positive, negative, or 0? That result is going to be 0. She continues to warm us up to the ideas of working with 0 and negative exponents with this next batch of problems. Number 12. And the instructions say, decide whether each expression is equal to 0, 1, or -1. So this is pretty much multiple choice. My answer will be 0, it will be 1, or it will be -1. What's the case here? What's going on? I have something raised to the 0 power. What is the base of that power? The whole -12. I've got this whole thing raised to the 0, and something to the 0 is 1. Now compare this to number 14. In number 14, I have -6 to the 0. What's the base? What's being raised to that 0 power? Just the 6. This negative out front is floating. He just floats into the next step. And we take 6 to the 0 and get 1. That negative is not participating as part of that base. Compare that to number 16, where we have -13 to the 0. What's the base of this exponent? just the negative 13 in parentheses. What's happening to this negative out front? Nothing. He's just floating. And negative 13 to the 0 is 1. All right, let's look at number 20. 0 to the 5th over 2 to the 0. 0 to the 5th, 0 raised to any power other than 0 to the 0. 0 raised to any non-zero power is 0. 2 to the 0, 2 to the 0 is 1. 0 divided by 1, there's no problem there. 0 divided by anything other than 0 is 0. If I had a 0 in the denominator, I would have a problem. That would be undefined, but that's certainly not the case here. Number 24. 2 to the 0 over 0 squared plus 2 to the 0. We crank this out order of operations. We work the top and bottom separately. When we have the top simplified and the bottom simplified, the last thing we'll do is perform the division indicated by this fraction bar. Working in the top, the only thing to do to the 2 to the 0 is 1. In the bottom, we'll take care of our powers. 0 squared is 0 plus 2 to the 0 is 1. You see where this is going. This will be 1 over 1, which is 1. All right. Let's crank this up another little notch. Let's look now at number 28. This is not multiple choice. We're simply asked to evaluate. Evaluate. 4 to the 0 plus 2 to the 0. Here in number 28. 4 raised to the 0 is 1 plus 2 raised to the 0 is 1. My answer here is 2. Number 30. 5 raised to the negative 4. We have been asked to evaluate. So we are going to crank this out until we get it down to just a single number. Hopefully you have noticed at this point, we never actually raise anything to a negative power. Not with arithmetic. We don't crank out anything that has a negative power. We interpret the negative power and then we crank it out. What does this negative mean on this power? It means take the reciprocal. 5 to the negative 4 is 1 over 5 to the positive 4. And 5 to the 4th, well, let's see. 5 to the 4th, here's what's happening in my head. 5 to the 4th power, well, that's going to be a 25 times a 25. If I've got 25 quarters, if I've got in change 25 quarters in my hand, what do I have? $6.25. 25 times 25 is 625. I don't care how you come up with it. I showed you how I came up with it. As long as you come up with that 625. My final answer here is 1 over 625. And by the way, I do not find that to be an unreasonable size number to give you on a quiz or a test. 5 to the 4th power, I think that's very doable. Number 34. Her instructions read just like mine. On a quiz or a test, this will say, evaluate, which means crank it out. Well, we don't crank out negative exponents. We interpret negative exponents and then we evaluate what we end up with. We know from our negative to positive rules that if I have a fraction to a negative, that's the same as its reciprocal to the positive. same as its reciprocal to the positive. Now, let me start evaluating. One way I could approach this is to say, well, this is a quotient to a power. I can distribute that power. Gives me 3 cubed over 2 cubed. And 3 cubed is 27. 2 cubed is 8. And that is in lowest terms. Let's have a look at number 38. And I'm going to tell you right now, I like number 38. Number 38 is a good problem. Before I write it down, I want to consider this. X to the negative 2 times y to the negative 3. How many terms are here? Terms are separated by pluses and minuses. Unless those plus or minuses are buried in parentheses, we're not talking about plus and minuses in exponents. Terms are members of addition and subtraction. There is one term here. This is a single term. It is a single product. And so, these share a fraction bar. X to the negative 2, and you understand this is over 1, so this is all in the numerator. X to the negative 2 in the numerator is x to the positive 2 in the denominator. Y to the negative 3 in the numerator is y to the positive 3 in the denominator. What's that leave behind in the numerator? Nothing. Our multiplicative nothing, that residual factor of 1. This is simplified. Compare that to this problem. X to the negative 2 plus y to the negative 3. Simplify. An expression is not simplified if it still has negative exponents. How many terms do you see here? This time I have 2 terms separated by the plus sign in the middle, meaning that they do not share a fraction bar. They each have their own fraction bar. X to the negative 2 is 1 over x to the positive 2, plus y to the negative 3 is 1 over y to the positive 3. What I see repeatedly is students will not look at those as 2 separate terms. They go, oh, negatives belong on the other side of the fraction bar. So my x squared goes in the bottom. And my plus, now, explain to me how that plus got sent to the bottom. That would not be possible. My y gets sent to the bottom because it has a negative exponent and there's nothing left in the top. No. No, this is absolutely wrong. 2 separate terms, 2 separate fraction bars. 2 separate terms will result in 2 separate terms when we're talking about dealing with those exponents. So bear this in mind now as we look at number 38. Six to the negative 1 plus 2 to the negative 1. I like this problem. This is a good problem. 6 to the negative 1 plus 2 to the negative 1. 2 separate terms. They each have their own fraction bar. 6 to the negative 1 in its own numerator is 1 over 6 to the positive 1 in its own denominator. 6 to the positive 1 is just 6. 2 to the negative 1 in its own numerator is 1 over 2 to the positive 1, which is just 2, in its own denominator. That negative indicates to take the reciprocal. And it's a negative first power, so that's the only thing it's going to do is take the reciprocal, because something to the first power is itself. Now to finish this off, of course we need a common denominator. 1/2 becomes 3/6. A total of 4/6 reduces to 2/3. I'm not teaching you how to do that part. It's this first step that I wanted to be sure and go over with you right now. Okay, having seen that problem, let's look at number 42. Two separate terms. So my next step should also have two separate terms, because all I'm going to do is interpret those powers. If I have a fraction raised to a negative, it's the same as its reciprocal to that positive. The reciprocal of 1/3 is 3. 3 over 1, we don't write over 1. And that 3 is to the what? To the positive first power. We don't write a first power. 1/3 to the negative 1 is just the reciprocal of 1/3, or 3. And plus, a fraction to a negative is its reciprocal to the positive. 3/4 to the positive first power. 3/4 to the first is just 3/4. Now, honestly, if I were working this problem and it came down to this, I'd be done. I'd write 3 3/4 and put a box around it. You're not always going to get so lucky. You're not always going to be so lucky in number 41 that you're going to be doing for homework. It won't be quite as clean as that. So remember how we typically will treat this in an algebra class. We deal with improper fractions more often than mixed numbers. We'd say that this 3, we're going to rewrite it as so many fourths, so we can add it to our 3/4. 3 is how many fourths? What divided by 4 gives me 3? 3 is 12 fourths. A total of 15 fourths. And when you look this up in the back, this is what you'll have. In this particular problem, I find nothing wrong with 3 3/4, but it's not going to always work out so cleanly. And so I encourage you to go ahead and practice doing it this way, keeping with our improper fractions. Now, let's take a glance ahead. On the next page, we've got some very busy problems, especially there in the middle and at the bottom of page 278. These problems in the middle and at the bottom. And what I'd like to do is put those on hold for right now. I want you to get used to dealing with these negative and zero exponents in the light of numeric problems before we begin tackling this next type of problem where we have variables running around all over the place. Let me do 2 more problems for you, but I am going to hold the homework as through number 41 for now. If you want to scoot a little past that, you'll see where we go. Let me work the next 2 problems for you, and then we'll call it quits on this for now. Number 58. Now, number 58 is a numeric problem. So that fits into the scheme of things that we're working right now. The instructions are on the bottom of the previous page. It says simplify each expression. Simplify, and that's all I would say. Simplify. We never actually evaluate a negative exponent. We interpret the negative exponent, and then we evaluate what we get. 6 to the negative 2 in the top is 6 to the positive 2 in the bottom. And in this same single term, they share a fraction bar, right? 5 to the negative 4 in the bottom becomes 5 to the positive 4 in the top. Now, if you remember from just minutes ago, 5 raised to the 4th power is 625. 6 squared is 36. 625 is nothing but a bunch of 5s. Is 36 divisible by 5? Certainly not. I guarantee that that's in lowest terms. But because it said simplify, I cannot stop here. while it still has exponents that can be worked out. Now, to get just a taste of what we are going to look at next time, let's look at number 62. And I'm going to go ahead and warn you right now. When it comes to these types of problems, there are many, many, many different ways to do most of these. Most of the time I will work it for you one way, the way that I consider the slickest, the way I consider the most obvious, the way I think most of us would approach the problem. But there are several of these I'll work it 2 and 3 different ways for you, just so you understand that as long as I don't break the rules, I'm going to get the same answer. Number 62, simplify. Well, I can do this a couple different ways. Actually, there are at least 4 different ways to work this one problem. 2 of them are approaches that I think most of us would choose from. I can look at this simply as a quotient of like bases. And when I have a quotient of like bases, I subtract the exponents. In other words, this is a to the 6 minus a negative 4. Well, 6 minus a negative 4, make 2 marks. That's 6 plus 4. This is a to the 10th. Some of us may see it this way. A to the positive 6 is good in the numerator where he is. A to the negative 4 in the denominator can become a to the positive 4 in the numerator. This is over 1 because what's left behind now in this denominator? Nothing, the multiplicative nothing. So it would be over 1. All I did was move this a to the negative 4 into the top where it becomes a to the positive 4. Now I have what? A product of like bases. When I have a product of like bases, I add those exponents. In each case, I followed the rules. It depends on how I see it, how I might approach it. But I followed the rules in each case and came up with the same answer both times. So, as we work in our next lecture on the balance of this homework, there are a few problems here and there that I'm going to say, let me work this 2 ways, let me work this 3 ways for you. And there will be some problems where I say, you know, there are at least 16 different ways. There are at least 32 different ways to work this one problem. There are enough different ways to work this one problem that I don't want to think about it. And we will try to stick to the slickest, the cleanest way to go about working these exponent problems. So for now, homework is going to be assigned through number 41. If you want to squeak your way up through 57 or 61, help yourself. But then kind of hold off there until we get to discuss more of what's going on in the rest of these problems. Homework assignment through 41. If you want to work up through 61, that's fine also. And we'll finish this section next time.